Lecture 8. So today we will pass the halfway mark of the course, so kind of big event in about 45 minutes from now. And what we're going to do today is, you remember last time we started with integration. We started quite gently. We said, okay, we defined really from the bottom what is a curve, what is a path, how do you integrate along paths, and so on. I want to clarify, by the way, so there was a question that I did not really understand what was meant by the question last time about the addition, so to speak, of paths. When I write gamma 1 plus gamma 2, what do I mean? Well, I really do mean this concatenation of paths, right? That you follow one path. I do not mean that you add them as functions, okay, if this was a confusion somebody had. And a second confusion, perhaps, so I noticed that I wrote in my notes Koshi's theorem for a disk, and then I wrote sort of by habit, I wrote the unit disk. Of course, it has nothing to do with the fact that it's the unit disk. You can do it for any radius. I mean, the proof is exactly the same, right? So this is another small correction. And if you remember, so we talked about winding number, and then we stopped in the middle sort of the proof of Koshi's theorem for a disk. And so we're going to start today by finishing this proof, and then we're going to look at all the consequences that this has. And we're really building the theory from the ground up. And this is important to emphasize as well, that I'm sure that most of you, if not all of you, know already about, for example, the residue theorem, which is an extremely powerful tool in complex analysis. And you can compute almost any integral I will give you. You can do it in one way or another by talking about poles and using the residue theorem. But we are not there yet in the course, and we sort of, I mean, in order to prove the residue theorem in a way that is not circular, we need to build the theory and what we're doing now. So we're not, it wouldn't make sense to use the residue theorem for anything I'm doing now, because then we are using the residue theorem to prove what we are then using to prove the residue theorem. So that would not work. And I guess the same remark goes a little bit for the homework, that of course, if I give you an integral and tell you to compute it, I cannot forbid you to use the residue theorem. It's okay. But of course, at this stage in the course, the integrals are much simpler and there are nicer, easier ways to do it. Even though, you know, the residue theorem could be very short, but it's an overly powerful tool to use for this. So in mathematics, usually you say that use the most basic tool that you can. For example, if you can prove something by some elementary argument, or you could see that it is implied, imagine somebody proved the Riemann hypothesis, and then this implies your result, then you don't want to give this proof if there's also just a 5-line elementary proof. Right? So you don't want to overuse the powerful results, such as the residue theorem, even though it's allowed. OK, so we were talking about Koshi's theorem for a disk. And the disk, I will write it D, but not the boldface D, because, as I said, it's not necessarily the unit disk. All I want is to have a nice, simply connected domain with nice boundary, nice topology. Everything is nice here. But the radius doesn't matter in any way. OK, so we have this theorem, which says that if f is an analytic function on the disk, and gamma is a closed curve, closed path, closed contour, but a closed curve in D, then the integral along gamma of f of z dz is equal to 0. Okay. So what it means is that we have some curve inside a region where the function is well-behaved everywhere. So there is no poles, no singularities of any kind, no weird things going on. The function is just as nice as possible inside a very nice domain. And then whichever curve you take, the integral will now be 0. And this is true even if you have self-intersections. As we said, if we imagine the figure 8, I could just treat this figure 8 as the sum of two parts, which are simple curves, right? And if I show that each of these integrals are 0, then also the sum of these two parts of the figure 8 will integrate to 0. So for the proof, you will remember that, so what we did last time was that we spent some time reducing the proof to the case of a triangle. Okay, so we reduced to proving it for a triangle, or for maybe I should write for triangles delta. We need to know it's true for any triangle, right? And we did this by approximating gamma using a polygon P, and then we triangulated the polygon. So what we had was that we have this picture of gamma. And again, so counterclockwise is the convention for positive orientation. And I could assume that it is a simple curve. Maybe I have a corner. Maybe it's not. It's only piecewise differentiable, right? So it could be allowed a corner. But I can assume it's this. And then what you did was that we approximated it with the polygon. Seems suitable to have another color for this. Okay, so we took the polygon here in blue. Okay, so we're doing something like this. Okay, this is P. And then we triangulated this polygon, if you remember, in such a way. So there was a rule for what we had to do. So what we wanted to achieve was that all the interior lines forming all these triangles, all the interior diagonals, they should be part of exactly 2 triangles. Okay? And the exception were the sides here on the polygon P. So, and we said that this was possible by always subdividing the thing by finding a diagonal such that the entire diagonal was inside the polygon except for the endpoints. And then we proceeded by induction. We said it was trivial for 3 and 4 edges, right? So we could divide it like this by finding a diagonal, and now we have 2 polygons here, each with fewer edges than the ones we had before. And then we could repeat the same procedure. So this one I subdivided into 2, and why not this one I subdivide into 2, in case they are more or less convex here. And so now I subdivide this one, then I subdivide this one, subdivide that. Here I can divide it like this, and like this. And now we have such a triangulation, I think, where each side is part of exactly 2 triangles. And the point of doing this, if you remember, was that it's quite ingenious, I think. It's quite beautiful. But now when we, well, first of all, the first step in what I wanted to write, of course, sorry? Sorry, can you speak a bit louder? So what we want to show, so the question is if all of this is independent of how we subdivide the polygon. So what we want to show is that the integral along the curve is 0, right? And now imagine, so now the claim, what we will prove later, is that for any triangle, it is 0. And so if I show that for any triangle it's 0, then I will sum up all of the integrals here. And then it means that for whichever polygon I take, it will be 0, and then this will approximate the whole curve, and it will be 0. So in what sense would you mean it should be independent of the polygon? I mean, you can take the triangulation in many different ways, right? And you can approximate the polygon, I mean, with different polygons in many, many different ways. But it doesn't matter, because whichever polygon you take, you can make a triangulation, and then the integral along every triangle is 0, so the integral is 0. And this is what we cared about. OK, and the point was, so first of all, we had that this integral along the polygon of f of z dz, it would, by refining the polygon by taking more and more edges. So we take the points closer and closer together here on gamma. So this would converge to the integral of gamma, to what we want. And then we will show that this one is always 0, however fine we take it. So since it converges to something, it has to also converge to 0. Okay, and then this one, we said that this one is equal to the sum of I of the integral along delta I of f of z dz, where delta I is now our partitioning into triangles. Okay? So these are the triangles. Oops. So they come from our triangulation delta I. Okay? And the reason for this, if you remember, is this very important fundamental trick in complex analysis that you see all of the time, which is that if you go once in one direction along a path and then come back in the other direction, then it cancels out. It's very elementary, but it means that, you can use this to move, to move from one curve to the other and show that the integrals are the same very often. So in this way, we saw that if we went around, always counterclockwise around each of these triangles, so here we have delta 1, delta 2, delta 3, and so on, all of them counterclockwise. So counterclockwise would be this direction. So let me put, first we have a polygon where everything is counterclockwise. You remember this picture. And then we went around counterclockwise for delta 1. So we go once like this. Then for delta 2, we go around counterclockwise. So it means that we get one in this direction. Okay. Then we get one like this and one like that. We go in delta 3. Then we have to go once in this direction and then once in this direction. So you see they've already canceled out here. And then when you keep doing this, you will get all of these arrows in the opposite direction. So if you keep going through all of these delta i's, so all of these sides will cancel out, but they will only get contributions by going once along the edges that were actually on P. And this is precisely why this equality here is true. Okay? So any questions about this kind of technique that I'm trying to explain? Because this is very key to do this kind of stuff. Okay, so all in all, this means that we reduced to proving the following lemma, that the integral of delta f of z dz is equal to 0, and this is true for any triangle. We have this, and gamma is the same thing as here. So gamma is any closed curve in a disk. F is holomorphic in this disk, and for any triangle, in particular inside this disk, we have this theorem here, or this lemma. And this has a name that I don't ordinarily use, but apparently this one is called, sorry? Morella. No, Morella is the, at least for me, Morella is the converse to Koshi's theorem. Yeah, but this is not the converse yet. So Morella would be if the integral along any closed curve is 0, then you're analytic. Yeah, continuous on the integrals, exactly. But this is not this theorem, right? This is a different theorem. So, or a lemma. And this is often called, so to be honest, I've never heard this before, but since it's a piece of history, why not write it down? So Bringheim's lemma. So it's not very clear what letter I wrote here. So Bringheim's lemma. Okay. So no matter this name, we now want to prove this. Okay, so proof. So how do we prove that for a triangle now, the integral has to always be 0? So we're looking at this triangle here. Counterclockwise, we want to know that the integral is 0. So now there is a second very common trick. I mean, the first very illustrative technique was this, how you can always create, reduce what you want to prove to some different shape by going along a path and then coming back along the same. The second one would be this subdivision technique. So a proof by subdivision, subdivision. Actually, what I want to say, sorry. I guess the correct term is bisection, actually. So what I want to say, of course, I will subdivide this triangle, but it's more precise to say bisection because I want to always subdivide it by taking the middle point on each side and then constructing a smaller triangle. Okay, so this is, I wouldn't say that it's obvious that this is how you should do it. Why should it work? But okay, I want to show that this is 0, so let me just take some smaller and smaller triangles and then go through some argument. But you'll see how this works as the proof goes along. So it's a proof by bisection, which is a common technique. So the first thing we do, step 1. So subdivide delta, which we will call delta 0 because we will have many different steps, right? So now we started step 1, step 0, whatever you want. But okay, we started with delta 0. So we subdivide delta into 4 parts. So we write delta is delta tilde of 1, union delta tilde of 2, union delta tilde 3, union delta tilde 4 in the following way. So it's easiest to describe it by a picture. So of course, you can write down in words, but what is the much easier since we're here with a blackboard. So but what I do is I take the middle point on each side. So this is why it's called bisection. Sorry, it's called bisection. And then I just form this triangle here by joining the middle points together. And now I get 4 triangles, right? So I get delta tilde 1, delta tilde 2, and so on. Okay? So I get these 4 triangles. And then what I do is the following. Okay, so first of all, we should note, by the way, note that what happens if I sum up the integrals along all of these triangles, well, something similar to this more complicated picture will happen. Okay, that the integral of delta of f of z dz is equal to the sum from I equals 1 to 4 of the integral along delta tilde I f of z dz. Okay, so in the same way, you can show this, that the integral is the sum, oriented appropriately, of course. And then the second claim is that we can pick, so one of these triangles, we can always pick a delta I, such that the integral along delta, sorry? You want to suppose for contradiction? No. In the proof? Yeah, possibly. So let's see how it ends, this proof. Let me just check. No, but it's not necessarily. Some proofs are by contradiction just almost as a matter of aesthetics, So what we will prove in this thing is, we'll get a sequence with something that goes to 0, and we'll actually show quite concretely, I think, that it goes to 0. But okay, so let us go through it, and if you still think you want contradiction, we go back and we write in red here, assume for contradiction it's not 0, but I don't think we'll need it, okay? So let us go through. So we assume that this is less than or equal to 4 integral of delta, so call it, pick a delta I, and we can call it, label it delta 1, delta tilde 1, okay? So of course, we can assume that it's the one that we label with delta 1, okay? Such that this, well, no, we call it, sorry, without the tilde. So we call it delta 1. Okay, so it should satisfy this. Now, what have I written here? So this is something this is just very basic logic, that I can pick one of the triangles such that this holds. Because I'm basically looking at the absolute value of each of these triangles, okay? And I say that since they sum up to this whole thing, there has to be at least one delta 1 such that the absolute value of this is larger than 1/4 of the absolute value of the whole thing, okay? Because if that's not true, then you cannot sum to something that's equal to this, okay? It's like saying that if I have 4 numbers that sum to 1, then at least one of them have to be, and they are all between 0 and 1, then at least one of them have to be larger than 1/4, or equal to 1/4. So we can find this, okay? And then we repeat the process. For delta 1. So we had delta 0. This was delta 0. Delta equals delta 0. And then we find a delta 1, which satisfies this. So what we do again is that, well, let's say that it was one of these triangles. So let's say it was the top one then, okay? The delta 1. Then we take the top one and we subdivide this one into 4 parts. We get a new subdivision into 4 triangles. Then we know that there has to be one of these that satisfies this inequality here, okay? And then we pick this one. So now let's say it was this. Okay, so we subdivide this one. We get a new subdivision into 4 triangles, and so on and so forth. Now let's say it was the middle one, okay? Yes, it was the middle one. So we get the subdivision into smaller and smaller triangles, like that. And eventually, the point will be that this converges sort of to a point. I mean, you will have exactly one point, which is in the intersection of all of these triangles in this smaller and smaller subdivision. And then we will use that we are holomorphic at that point. Okay. So this is how the idea of a proof will go. So repeat the process. So we get the sequence. So delta 0, which is the largest one, so it contains delta 1, which contains delta 2, and so on. So we can repeat this infinitely, okay? So we get this sequence such that this delta 0 so okay, I'm writing slightly smaller. I hope you can see. Can you see, actually? Can someone not see? Good. So this is less than or equal to 4 to the power n. So now by induction, this, okay, times the absolute value of the integrals of this delta n f of z dz. Okay. So we get this kind of thing, but we put an n here, and we put an n here. Otherwise, it's exactly the same inequality. Okay, and of course, you see how you get this. I mean, clear, I hope. Okay, so we get this sequence, and moreover, if we look at the size of this subdivision, so what is the perimeter and what is the diameter of these triangles? Okay, so the perimeter of delta n. So every time, so since I do this subdivision where I divide each side of a triangle in exactly half, then basically all of these measures of perimeter and diameter, they will be exactly divided by 2 as well. So this is, again, then, so compared to the original delta 0, I will slash it by half n times, so I will get 2 to the power minus n. Sorry. Of course, it's the perimeter here. Here it's the diameter. Can remove those parentheses. Okay, so we get this. But most importantly, we get that if we look at the intersection of all of these triangles, okay, so what is going to happen? So each 1 point, exactly, because we have an intersection of infinitely many closed sets, these triangles, right? So the intersection will be some closed set, and there will always be 1 point which is inside all of them by the construction. So this is going to be equal to some point which we call Z0. I mean, this is a very special point for some Z0 in the original triangle, delta 0. Okay? So somewhere inside the original triangle, there is a point to which all of this bisection process converges in this sense. Okay? And now we use that f is holomorphic in this point z equals z0. So this means that we can pick some natural number n such that the following holds. So if I write down f of z minus f of z0, so I write down this quotient, which is supposed to converge to the derivative, right? So if I write down that and I compare it to f prime of z0, then since it is holomorphic, then this is supposed to actually converge to this. And everything is well defined in particular, because I can talk about f prime since f was assumed to be holomorphic. Okay, so this less than epsilon. Who is epsilon? Did I write down epsilon on the board somewhere? Sorry? Yeah, probably. This is what I wanted to say. Yeah, maybe. Okay. The point is anyway, however way you want to write it, the point is that it's small. Okay? Right. So this is what I wanted. Okay. So then we can write that. So by rewriting this kind of thing, we can say that we can write something that looks like a power series expansion. Okay. So f of z0 plus f prime of z0 times z minus z0 plus this kind of remainder term which is small. Okay. So less than epsilon, but I guess that would be then the 1 over n, which is my epsilon. Now, okay. So we get this, and this should be true for any z in delta n. Okay. So what we are saying is that if we are in delta n, then we are close enough. Yes. Yeah. Okay, so epsilon, 1 over n, whichever you want. The point is anyway that if you take n sufficiently large, then you arrive close enough to this z0, which is in all of these triangles, such that this one is small. And if this one is small, then this first order approximation of this thing is close to being the correct value, meaning this error term here is small. Okay? And this is true for all z in this set. And then, what do we get? Let me maybe continue here. Okay, so now we want to write down this integral along delta n is then equal to the integral of, and now I'm replacing f of z with whatever I wrote over there, okay? So these three different terms. So it's the integral of this f of z0 plus f prime of z0 times z minus z0. Okay, so far, so good. And then we get also this error term. So r z minus z0, r of z dz. Okay, and now let's see what we can say about the value of these things. So the first question is, what is the value of this integral, this first one? Aha. Exactly, this is a constant. So, I mean, everything is constant except this thing here, right? Yeah. Yeah. Exactly. So the remark is that actually this thing here equals to 0. One way you can see it that relates nicely to the last lecture was that we said that if you have a primitive function, then the integral has to be 0. Because then you get this analog or extension of the fundamental theorem of calculus. But if you have a primitive and your curve is closed, which is definitely the case with this triangle here, then you get 0. So 0 because integrand has a primitive or antiderivative. In Sweden, we call it primitive, so I will tend to write this, but you can follow. So, okay, and then we have this, so we have this part, which is left, right? Let me just circle it. So we are left with this part. And now what do we do with this? Well, it means that we can now do the other standard thing, which is super standard in complex analysis, is that you always write down the absolute value of something, and then you put the absolute value inside, right? This is the estimate I remember using over and over and over again whenever you took this course. So this is less than or equal to delta n, and then you just write down whatever is there. So absolute value of each of these things. This is a key thing that you have to put the absolute value also on dz. This confused me a lot, I have to admit, when I first took my first complex analysis course as an undergrad. I thought, okay, wow, I never seen this, what do you mean, absolute value of dz? But okay, you have to put it. It means that you will now, whenever you take the integral of dz, it will then just be the length of this curve, which is then the perimeter of the triangle. This is what is meant by this measure. Okay. And if you're not confused about that, like I was when I took my first course, this is not your first course either, then, just go on with your understanding of this. Okay, so what is this? So it's less than or equal to this 1 over n. So let's see, will this work with, yes. Okay, so it's less than or equal to our epsilon, our 1 over n, times the integral of, so now I just use that this was less than 1 over n, okay? So less than this, but then we also have, so this was because this one is less than 1 over n. And then we have this z minus z0 here. Well, this is less than or equal to the diameter of delta n. Okay? Because both z and z0 are in delta n. So this is less than or equal to 1 over n times the diameter of delta n times the integral of delta n of this. Whoops. But this is equal to then the perimeter of delta n, right? Perimeter is the length of the sum of all the lengths of the triangles. Okay, so this is what is meant by that. And then this is equal to, so it's 1 over n times the diameter of delta n times the perimeter of delta n. But then we wrote on the other board there that because we exactly subdivide each side into 2 at every step, these things will be divided by half at each step. So this will be equal to 1 over n, 2 to the minus n times 2 to the minus n. So I get 4 to the minus n. Diameter of delta 0 times the perimeter of delta 0. And the good thing is that these do not depend on n, right? So now we can study. Okay, so what I did now was I estimated the absolute value of delta n, okay? But what I had, if you remember, was that this absolute value of delta n, it was greater than or equal to 4 minus n times delta 0, okay? So summarizing, so to now add up what we have that the absolute value of the original triangle, this one is less than or equal to 4 to the n times delta n f of z dz, which is then less than or equal to 4 to the n times all of this. So it will cancel out this part. So which is then less than or equal to 1 over n diameter of delta 0 times perimeter of delta 0. And this goes to 0 as n goes to infinity. Okay? So what we have shown is then that the absolute value of our integral is always smaller than 1 over n for each n. Okay? So the absolute value has no choice but being 0. And if the absolute value of a complex number is 0, then the complex number itself is 0. There is no other choice. So this then finishes the proof. It shows that the integral of delta, but this integral here, integral of delta f of z dz, is equal to 0. Okay? Any questions so far? While I erase this, you can think about possible questions. Okay, great. So we proved Koshi's theorem, and we didn't need to do it by contradiction, right? You agree? So, but of course, many proofs are possible to formulate by contradiction if you want to. So this is a whole different story. Okay, so now we got the Koshi's theorem for a disk. Okay, but it's also possible to prove a more general version of Koshi's theorem. Okay, and to prove this more general version, this is when we remember from last time that we were talking about winding numbers, and this is where the winding number comes in. But another thing that comes into the hypothesis is the notion of a curve being homologous to 0. Okay, so you know about curves maybe from topology, I don't know, that are homotopic to 0, or maybe this comes only in algebraic topology. I don't know if you saw it in the topology course or not. Did you? Do you know curve homotopic to another curve? Yeah. Yeah, it's okay. You don't have to give a definition, but you know what it is. I don't know if you saw it in the course. Okay. But now we're going to not talking about homotopy, but homologous to 0, okay? So this is a different thing. We're going to see one example of one which is homologous to 0 but not homotopic to the trivial path, okay? So definitions. Okay, so just a few definitions here, 2 definitions to be precise. So a closed path gamma in some open set U, so a subset of C, is said to be homologous to 0. And what we write it like this, gamma tilde, the twiddle, or gamma tilde 0, if the winding number is equal to 0 for all points A not in this open set U. Okay. So if the winding number is 0 outside, and we will also remind you maybe what was the definition of the winding number. So it was 1 over 2 pi I, the integral of dz over z minus a along gamma. So this is the winding number of A. And you remember we explained in great length last time why this was a natural definition. Okay? This was the winding number. And then I want to, so the point of introducing this is also that I can now tell you what it means to be simply connected. Okay. So this, a set U, which is open and connected, is said to be simply connected if every closed path gamma in U is homologous to 0. Okay, so I will give you examples to illustrate these 2 definitions. So a path being homologous to 0, and if every path is homologous to 0, then we say that the set is simply connected. So this is one way of characterizing this. So if you look at this, so simply the disk of radius r in C. So it's an open connected set. So this one, is it simply connected? Well, yes, correct. So this one is simply connected, and why? So one way to say this is by Koshi's theorem. Okay. And why do I say this? By Koshi's theorem. Exactly. So I'm looking at the integral. So what I have to do is I have to look at this integral dz over z minus a, and I want this to be 0. So gamma is some curve inside here. And then I want to take a outside of my disk, right? Outside of U. So a is here. And that means, so if it would have been a totally different story if a was inside. But now a is outside, which means that 1 over z minus a does not have any problem, so to speak, does not have any pole inside this domain. So this is holomorphic everywhere inside the curve. So it means this one is equal to 0. So of course, if I multiply by 1 over 2 pi I, it changes nothing. And this was precisely our winding number, which if you go back to definition 1, this is what we wanted to prove for all a outside of the domain. Otherwise, it would have been a different thing. So by Koshi's theorem, this one is simply connected. Second example, if I take the same disk, but I remove 0, is this one simply connected? Okay, correct. So the intuition is it's not simply connected. And what would be the argument? Sorry? Yeah, but if we look here, so we want to see if it's not simply connected, it means we can find a point A outside of our domain suddenly, such that this kind of integral is not 0. And here I claim that we can easily see which one is the point A we want to use. So here it was simply connected. Now we removed 0. All of a sudden, it's not simply connected. Well, it's because there was a problem by removing a point inside the disk. I could have removed another point inside the disk, by the way, not just the central point. So the proof is take A equals 0. And then, of course, this integral of dz over z minus a will no longer be 0. Okay. So we have that. Oh la la. Okay. So then we have a third example, which is by far the most interesting example. So now to a more complicated one. So take U to be this, to be C, where we remove 2 points, 0 and 1, or whichever 2 points you want, to be honest. Okay. And then I will try to draw a picture of this path that we will consider. Okay, so then we can draw the following picture of the so-called, so I'm not sure how this is pronounced, so Postgraduate path. So you remove 0 and you remove 1 from this complex plane here. And then you draw, very carefully, you draw the following picture, okay? You draw figure 8 like that, figure 8 like that, and then it's supposed to come back. Okay. So sorry about being so close to what I wrote, but so we have this path here. Okay. And so it goes like this, just to follow it. Then it comes up here, goes like that, comes down here, and then like that. So this is the programmable path. And the claim here is that this path, so this one is homologous to 0, but not homotopic to the trivial path. Okay, because otherwise you might get the impression that all the ones that are simply connected is something where you can take any curve and you can just shrink it to 0 while staying inside the domain. But this is not true. This shows that even if you remove some points inside, it's not automatically that you cannot have curves that are, I mean, you can have this kind of more complicated thing that are still homologous to 0, even though you cannot shrink it to the trivial path continuously in the sense of algebraic topology. And the reason for that, well, it's that if you count how many times they wind around these curves, so the reason is that the winding number at 0 is equal to the winding number at 1. I mean, they are both 0, actually. Because you see you go around once, so to speak. You will go around once if you check it in this direction, in the clockwise direction, and then you come around once in the counterclockwise direction. This is sort of going to be the intuition. This is going to happen in both these cases. So actually, you can check this, that the winding number is 0. OK. And so those were a few examples. And now I can just state the more general form of Cauchy's theorem. Or actually, I could even say more general forms, because I will give two. So theorem 1 would be that if F is analytic on U, some simply connected, so this is what we just defined, of course, this was the point. So U is a simply connected open region, so open set in the complex plane. And now if gamma is a closed path, which is homologous to 0, so let me just write it like this. Then, so homologous to 0 in this set, in U. Then it is still true under these much weaker conditions that the integral is 0. Okay, so if you have a closed path homologous to 0 in something, then this is always true. So this proof, I will not prove this one here. Okay, so if you want the proof of that, there are books that cover this. But again, which I gave this speech last time, that this business of always going to push it to the most general version is not really the point of this course. Like there's always a little further you can push it, right? But I still think it's very important that you know this statement that it exists and this is possible. Now, if you want the exact proof, then the ideas are always kind of the same. We went through the proof where we started with some fairly general situation, then we approximated by polygons, and then we reduced it to a triangle. Now, if you do this business, then you just have to find even more clever ways to reduce it to something you know. Okay, morally, this is what you do. Okay, so for whoever is interested, this exists in various sources that can show you this. Okay, and in particular, just as a small remark, note that by Cauchy's theorem, that this implies that if we have two paths, gamma 1 and gamma 2, such that gamma 1 of the starting point is equal to gamma 2 of the starting point. I mean, they start and end at the same point, okay? These gamma i's are parameterized on AB. Then, by Cauchy's theorem, if you take the integral along gamma 1 and then minus gamma 2, then it has to be 0. If I go like that and like that, then we have a path to which our Cauchy's theorem applies. Here, they are not differentiable, but this is certainly piecewise differentiable if I take smooth curves. So by Cauchy's theorem, the integral along gamma 1 minus gamma 2 of some function which is holomorphic here on all of this domain is equal to 0. And this implies, the integral of gamma 1 minus gamma 2 is equal to integral of the gamma 1 minus the integral of gamma 2. So this implies that integral of gamma 1 is equal to the integral of the gamma 2. Okay, so we get this independence of the paths where we integrate. Unless, of course, we have some problematic point of our function inside here, then maybe, Cauchy's theorem will not tell you that this is 0 anymore. And then we will not have independence of the paths if we maybe go on different sides of a pole of our function. So it is not holomorphic everywhere. But if it is holomorphic in a neighborhood of this whole picture, then we have independence of the paths. So just to point out, as a side remark, this consequence. And then I want to go to the next topic, I mean, very, very closely related, but a nice application of this formula will be Cauchy's integral formula. Okay, now I have a choice because I have a second improvement of Cauchy that I could point out. So should I do that? Yeah, let me do that. So let me write theorem 2. A second improvement of Cauchy. And this will turn out to be a kind of important improvement, actually. This one is important for the proofs that I will go through to come. So if R is a, so this one talks about rectangles, but it's not so important if it's a rectangle or some other shape. I mean, usually you can reduce it to one or the other. Okay, so in C, and let Z0 be a point in this rectangle. So suppose that F is analytic. So now not on the rectangle, so let me draw the rectangle. Okay, so this is R. And then you have some point Z0 inside this domain. But now I want to just loosen very slightly this hypothesis that F is holomorphic everywhere. So if it's analytic on R prime, which I then take to be R, but I remove this point, okay? So I take away this point. It's holomorphic everywhere, but it has some problem here. Maybe it's 1 over Z minus Z0, something like that. Then, okay, so if we assume one more condition, that we limit as Z goes to Z0 of Z minus Z0 f of Z, if this is equal to 0, then actually the Cauchy's theorem along this rectangle still holds. Okay, so this thing here is what is called, it's called something if you have seen about singularities. Yes, I hear somebody say a removable singularity. That is correct. This condition here is what is called a removable singularity. So now, make no mistake. So later on, actually quite soon, probably next lecture, we will show that if you have a removable singularity, then the function is already analytic. So soon we will be able to prove that this condition implies that F is in fact analytic in all of R, and then we apply the usual Cauchy's theorem. Okay? But we cannot do that yet, because to prove that this one is analytic, we need this theorem, right? Or we need another theorem for which we need this theorem to prove that theorem. So really going from, again, from the bottom up, we have to start by proving this kind of statement. But for later in the course, we will just say this is a removable singularity, so F is analytic. But to understand the proofs, we need to go through this thing. Okay? So the proof that it can be defined in what? In Z? Sorry, a bit more. Sorry.
We redefine the function at the
You mean in this theorem that will come later? Yeah, exactly. Yeah. So in the theorem that comes later, we will realize that we can just let the value in this exceptional point be exactly something, and then this gives something which is holomorphic, so in particular continuous. Yeah, so we will explicitly put the value in this Z0. We'll be able to do that later, but not yet. Need some more preparation. Okay, so the proof is, again, that, so I will do this proof, I mean, if you'll allow me, again, I will use a lot of pictures and talking. So here is R, and here is Z0. And let us subdivide this in such a way that we get this to be R0. So this was R, and this thing here, we call it R0. So it's a small rectangle or even a small square, we could assume. Okay, and then we do the usual business with going back and forth. When we sum up the integrals along all of these triangles, again, you see each edge is in exactly 2 of them, which is the magic indication that this argument will work. We see that when we take the integral along the boundary of R, so the boundary of this rectangle, the large rectangle of f of z dz, then it's equal to the integral along the boundary of the small rectangle or square, f of z dz. Okay? And now, the point is that I want to choose R0 simply small enough. So now I want to use this hypothesis, right? So I know that the limit of this times f of z is 0. So how can I use it? I use it in the following way. So by choosing R0 small enough such that the value, absolute value of f of z is less than or equal to epsilon over absolute value of z minus z0. So this is a sort of reshuffling of this condition, right? That the absolute value of this times that has to be less than epsilon eventually when z comes close enough. And this should be true for every z in R0, okay? Where now the radius depends on epsilon, okay? So of course, I could write this a little bit more properly. I could say that this epsilon is equal to 1 over n, where 1 over n is the side length of R0 or something like that. But the point is you understand what I mean when I'm sketching this argument. So this is possible by this hypothesis star here, okay? And then if we call this thing here, if we call this double star, so now double star implies that the absolute value along the big rectangle, okay, so this is equal to the absolute value along the small one, but I do 2 steps at once. So I also put here the absolute value inside. Okay. And then the absolute value of f of z is now less than or equal to this epsilon over absolute value of z minus z0. So this is less than or equal to this thing. And now all I have to say is that this is bounded by some constant. And so I indeed claim that this is less than or equal to c times epsilon, where c here is a completely uniform constant. So this is important. And claim is that if R0 is a square, then I can take c equal to 8. Yeah, this one is nice. So, I could do it here in 2 lines, but I actually think it's nicer if you just think about it because it looks surprising. But basically, the point is that you have this picture here, you have Z0. You can assume it's in the middle of the square, just to see what I mean. And Z here is on the boundary, right? Because I'm integrating over the boundary of R0. So Z is here. So, of course, there is a bound for how close together Z and Z0 can be. And this is all I'm saying, right? And actually, what I'm saying is that if this side length is x, then you see that 1 over absolute value of z minus z0, it's less than or equal to 1 over x over 2, which is equal to 2 over x. Okay? Because, of course, the shortest possible, if this is indeed a square, I cannot get closer than x over 2 from here. Okay, so this is 2 over x, and then what I have is that, so if I continue here, so integral along r0 of dz over z minus z0 is less than or equal to 2 over x times the integral of dz. But what is this? This is just 4x, right? The side length was x. So this is equal to 2 over x times 4x. And the x's cancel, and this is precisely 8. Right? If I assumed that my picture was in such a way that I took a square always, which definitely I could. You see, these subdivisions, you have a lot of room for defining yourself what you want to take. Then you could take this equal to 8. If you didn't take it as a square, you'd get some other constant, but there would always be such a constant. OK, so now we saw that we can improve this Cauchy's theorem for a disk in several directions. So we said it was enough to have a simply connected domain and then a path homologous to 0. But we also saw that it was enough to consider these functions with this removable singularity condition, which again, in a week from now, this will be obvious to you because you'll say it's analytic and you'll just apply Cauchy. But we need this to prove the next theorem, which is the Cauchy integral formula, which is a very closely related thing, right? Which involves, by the way, the winding number. So this is a nice thing. This is an application of Cauchy. Of Cauchy's theorem. OK, so the statement of this is as follows. So suppose that f is analytic. And now I go back to considering these disks, right? Again, not optimal regularity, but let me do that. This is what we do in Alfors as well. So it's analytic in an open disk. D and gamma is a closed curve in D, closed path. Sorry, what was the question? No? For any point A, and here comes a rather important condition. So you cannot allow this point A to be on the curve. Right? It can be inside, it can be outside, but just not on the curve. And usually, if it is on the curve, you just move the curve a little bit, and typically, you can work with that. So if it's not on the curve, then we have the following formula. Okay, so 1 over 2 pi I, integral along gamma of f of z over z minus a dz. OK, so this is Cauchy's so-called integral formula. The most common applications are when you take maybe a circle winding around A once, so that this will be equal to 1. And then you will get that f of A is equal to this kind of thing, which is an often used formula. And one of the really nice things about it is that it can be viewed as a representation formula. OK, so I will talk about that in a second. So first, let me just remind you. So reminder, So I'm not actually sure if I said this last time. So if I didn't, then it's not a reminder, then I'll just remark it. So that if A is not inside the disk, so it means that, okay, you're holomorphic inside the disk, but now you take A to be far away, then what can we say about the winding number? So what do you think? It's 0, right? And this is true then this is what we would call the connected component of infinity. So every curve divides the plane into multiple connected components. And we have one, which is the connected component of infinity, which is outside of everything. And then this winding number has to be 0. Okay. So there is something like this on the homework. So yeah, the most common application is when this thing is equal to 1. So now let us prove also this. So we are doing a lot of proofs in rapid succession here today of all these integral theorems. So how can we prove this? So proof. So the proof is that we want to come up with some smart function to which we can apply Cauchy's theorem. Okay? And of course, to figure out, okay, exactly what function do I need to put to get this, okay, you need to sit down and think a little bit. So I will tell you that apply Cauchy's theorem to the following function, to f of z, which is f of z minus f of a divided by z minus a. So for some reason, I mean, we tend to often look at this function when we prove this kind of theorems, this difference quotient, which is supposed to then have as a limit the derivative in this point. Okay, so we look at this function, which, I mean, is it analytic? Yes? Okay, yeah, you're right. Exactly. So the answer is yes, because it's a removable singularity at z equals a. But so far, let's say that it's analytic for z not a. I mean, you're right. It's analytic also in z equals a. But let's do it in 2 steps. This is all I'm saying. So it's analytic there, clearly. But also, so in z equals a, we have the limit of this z minus a times f of z is then limit of f of z minus f of a. Well, of course, what is this limit going to be? It's going to be 0, right? So this is equal to 0. So it means that we have a removable singularity, but we don't know that yet. All we know so far is that we can apply this theorem 2. Okay. So by theorem 2, on the last board, this implies so to apply it, sorry, of course, this was for a rectangle, right? So we want to apply it. So how can we apply it to a rectangle if we have in general some curve? So in general, I have this curve. This is my gamma. Now, I want to apply this theorem. Exactly, okay, we take a rectangle around A. This is R. Exactly, and then you do this thing where you sort of cut and you go in and you go out on the same path. And then we know that, so this was gamma, this was R, and this one, let us call it gamma tilde or something. And then we know that if we take the integral along gamma plus gamma tilde, and then we go R, but in the other direction, right? So minus R. This is the only tricky thing, you see. because here we're going counterclockwise, so it counts with plus. When we go in, we then arrive here going maybe clockwise, so it's minus r, okay? And then when we go out, it's minus gamma tilde. So this is equal to 0 by Koshi, okay? And then 0 is equal to the integral of gamma plus the integral of gamma tilde minus the integral of gamma tilde minus the integral of r. So, sorry? Exactly. So what we get from such a picture is that first note that the integral, okay, so can take R a small rectangle. So I say it's a small because I want it to be small enough so it's inside of gamma. Okay, I don't want any funny business. So the small rectangle around A, around my point A, such that the integral of gamma f of z dz is equal to the integral along the boundary of this rectangle, first of all. So this was this picture. But also this, now by theorem 2, this is equal to 0 as well, right? Okay, so this means that the integral of gamma is 0, also in this case. And now to finish, so in other words, we have 0 is equal to the integral. Okay, so here I wrote with small f, but of course, the function I want to apply it to, sorry, is capital F now, because this is my holomorphic function I study, right? So not to confuse. Okay, so the integral of gamma of f of z dz. But this is equal to what? Well, it's just equal to gamma of f of z minus f of a over z minus a dz. And then we decompose this step by step. So now I write it like this. Okay, so on one hand, I have this integral. And on the other hand, I have minus f of a, which is just a number, of course, times the integral along gamma of dz over z minus a. Okay? And now, what is this? So this thing here exactly, it's even 2 pi I times n of gamma of a. So it's equal to 2 pi I times n of gamma of a. Okay? So this is the key remark. Now let's just try to remember what we wanted to prove. We wanted to prove this formula, right? Okay. So 0 is equal to this minus 2 pi I n of gamma of a f of a. So rearranging this gives exactly that. Okay. So hence we prove Cauchy's integral formula. And now, in the last something 10 minutes, let me tell you why this Cauchy's integral formula is so great. Okay, so it is so great because we have, first of all, we get from it higher derivatives. And we also get this thing called representation formula. Okay, so this theorem 2 now, I think we used it, by the way. We used it to prove Cauchy's integral formula, and then we will later prove that if you have this condition that the limit of z minus a times f of z is 0, then it will actually be analytic. So then we don't have to remember this forever. But you can remember it has to be there to prove the whole sequence of things. OK, so so now we are in the same situation as on the board over there. So I won't always rewrite it, OK? So we are analytic. We have an analytic function f in some large open disk, any radius. We have a closed curve gamma inside. And we have some point A which is not on the curve, OK? So if we assume now that the winding number is 1, so for example, we take a circle counterclockwise around A. There are many other choices too. Then this Cauchy's integral formula, which I write like that now, can be interpreted as a so-called representation formula. And what I mean by that is the following. Is that if I want the value at a point of my function, then I can integrate across some sort of kernel here and get out the value of my function. So, of course, here there is a hidden 1, which is equal to, so this is true whenever, if this is 1 for all z inside gamma or something like that, OK? Yeah. So this is true for any z such that this holds. Sorry, so let me write it like that. OK. And now what we want to do is we want to get from this the expression. So we express f of z as this integral. And now imagine what would f prime be. So we don't know yet, remember, we don't know yet that we can differentiate infinitely many times. I mean, what will the differential be? Rather, we don't know that we have a power series expansion of holomorphic functions. So if we want an expression for f prime of z, then what should it be? So the point here is that if we could justify that we can differentiate under the integral sign, then we should have, OK? So then we should be able to obtain the following formulas. So then we should get f prime of z, which would be equal to what? So then we would get f prime of z is equal to minus yeah, there are two minus, it's a plus, yeah. So it should be equal to f of w over w minus z squared dz, and so on. We should get that fn of z is equal to n factorial over 2 pi I integral gamma f of w over omega, w minus z to n plus 1. This is a habit, you know. I wrote dz so many times in this course so far that it goes automatic, but it's dw, OK? dw. So then you should get these formulas, and this is true for any n. So you should be able to differentiate like this. Of course, again, assuming, so if z is in a connected component, so of course when you differentiate, you need to know what happens in the neighborhood of your point. but we know that this winding number is invariant. I mean, it's constant on the connected components. So really, being inside the connected component where this holds, we have this kind of formulas. Now, as I said, this is a big if, right? So if we could differentiate under the integral sign, then we should be able to get this. So in order to get these formulas, we have to justify in some way what we get. Okay, and for this, I will just write down a few comments. Okay, so it is here. So to justify this, we need the following. It's a lemma. So we need some general lemma, which says that suppose, it says the following. So suppose phi of w is continuous on an arc gamma. So an arc means it's not necessarily closed. Okay, so we have some gamma here, sufficiently regular. Then the function, following function, fn of z, defined by such an integral. So we want to look at such an integral and see if we can differentiate it. So we will write this down, or fn will be the nth integral here, up to removing the constants. So then having an integral of this form, okay, so you see it's exactly up to a constant what we want to differentiate. So this one is analytic in C minus gamma. So I remove gamma. So it's analytic except if we're on gamma. And we can get its derivative in the point z by the following formula. And as you can see, this is precisely what we need. So you see fn of z is equal to, well, actually, yeah, it's equal to this fn minus 1 derivative, right, times a constant. And then when you differentiate it, we just want to see that, okay, when we differentiate, then we want this constant n to come out, and then to increase this to n plus 1. And this is precisely what this formula says that you can do. Okay, and this one was one of the exercises that on the homework sheet, but whose fate it was to be not mandatory to hand in. So this is one of the removed exercises, so, but not mandatory for hand in. Okay, but it is there anyway because I want you to justify it, but I thought it was a good one to remove because you have to write a little bit and it's kind of annoying if you don't have much time. Okay, but you can have a look at it. So actually, not very well-guarded secret is that you can find this in Alfors on page 121 or something. I don't know, something like that. If you also want to read it, since you're anyway not going to hand it in. Okay, so the punchline, let me end by this. The punchline is the following. is that we have now shown that analytic functions are not only differentiable, right? So analytic holomorphic, right? Holomorphic was defined to be complex differentiable, so we know it's differentiable. But we don't know that f prime, so we have a derivative, but is the derivative differentiable? Is it holomorphic? Well, we don't know yet, right? But now we do. So now we have shown that, okay, f prime, so if f is analytic, then f prime is equal to this. Okay, but then we have also shown that all of these derivatives are actually analytic, because this is what they say. Fn is always analytic here. So analytic functions, yeah, and then I can in particular differentiate again and again and again, and all of them are analytic. So analytic functions are infinitely differentiable. You can differentiate as many times as you want. And you even have these nice explicit formulas. And the derivatives themselves, so this is a bit tautological, okay, infinitely differentiable should imply that the derivatives are then analytic, but it's still worth to point out. So the derivative themselves are analytic. So I can put this in parentheses. Okay. And they are given by these formulas that we just proved. So these formulas over here. So it is very key that we know that the derivatives themselves are analytic. So we'll see how to use this next time to prove various theorems. But just let me tell you in words that, for example, now, if we want to show that a function is analytic, then it suffices to find a primitive, actually. So if we have some function, we don't understand it, but we know that it's the derivative of some function, which we can show is analytic, then now, thanks to this remark, we know that, okay, I'm the derivative of an analytic function, so it has to also be analytic. And this will be the idea of the next proof, which is Morella's theorem that was mentioned earlier, which is then a converse to Koshi's theorem. So we'll start next time by unleashing all of this sequence of corollaries of this Koshi's theorem and Koshi's integral formula. So we'll show the converse, and then we'll show Liouville's theorem, Koshi's estimate. We'll give a nice, 1-minute proof of fundamental theorem of algebra. And then we will start talking about these removable singularities and so on. Okay, so this is the plan for the next time of the course. Now my time is up, so I'll stop here. So if you have any questions, of course, feel free, as usual.
Hello.
Yes. Hello, Younes. No, yes.
Is it true that every analytical function has a primitive?
Is it true that any analytic function has a primitive? This is your question?
Yes.
Yes, it is true.
So can we conclude from this directly the Koshi theorem?
If we can prove, if we knew that every analytic function had a primitive, then we would get Koshi's theorem. Yeah. So then we would get it, as we remarked in last lecture, indeed.
I order.
Yeah.
Okay.
Yeah. So again, everything is about the order of things. So we needed Koshi's theorem to be able to prove Koshi's integral formula, which would then prove that any analytic function has a primitive eventually. And yeah, so we still need to be careful about the order when we take the course. But a posteriori, as we say, you can do that, yeah. But if I ask you to prove Cauchy's theorem, it would not be a valid proof because you then use Cauchy's theorem to prove itself, right?
Yeah.
Right. Exactly. Okay, any more questions?
Also, I didn't quite understand why does the approximation of polygons, why the integral on the polygons tends to the integral on the curve.
So the curve is piecewise smooth, right? So you don't have a fractal curve or anything like that. So
again, we can approximate the curve, but why are the limits on the integral the same?
Well, I mean, this, so I never gave the details of this, but I was thinking that it should be intuitively, I mean, it should be fairly clear, no? I mean, you approximate the path and the function and everything is very nice, so then this should hold. But okay, I can understand your criticism that you would want some more details on this point. So it is true, I didn't give all the details. But I think it's very believable, and you can sit down and write it down, no?
Okay.
Yeah. So Younes, are you in Trieste, by the way? I saw you handed in on ICTP paper.
Yeah.
Yeah.
My quarantine was supposed to end today. But,
Okay.
Yeah, but then they didn't receive the results or something like this.
Okay. Good. So we'll see you next week, and maybe.
Yeah, hopefully.
Okay. Very good. That'd be nice. Another one. Is anyone else in Trieste? I mean, Ruba, I guess you're in Trieste as well. And then
Yeah.
Are you in quarantine now?
Yeah, I did the test yesterday, and I'm waiting for the results also.
Okay. So I'll see maybe you also next week then. That's good. Yeah. Okay, cool. So any other questions? Okay, so then, yeah, good luck with your studying for topology exam and midterms in real analysis and all that you have to do. And then I hope it's reasonable with having removed the exercises where you, I mean, I removed the exercise where you had to write the most, actually. So I hope it's fine, that it should be reasonable. To hand in something, right? To think also about complex analysis a little bit until next week. Okay, so have a good weekend and see you next week.